This is the week 5 workbook. In this week, we are going to review capacitor and also we'll introduce inductor. A capacitor is constructed with two metal plates, and when these two metal plates connect to a voltage source, the charge will accumulate on both sides of the metal plate, and there will be an electric field developed across these two metal plates, and the charge it holds per each voltage is what we define capacitance. And the unit of capacitance therefore is coulomb per volt, or we call it Faraday. So next is what determines the capacitance of the metal plate, and experimentally we find the capacitance of these two metal plates is proportional to the area and inversely proportional to the separation D. So this is the D, and the proportional constant is epsilon, and this we call permittivity of free space. And this is a universal constant here. So this is our basic definition of capacitance. And this is the unit in Faraday. Now if we rearrange the definition, Q equal to CV, and we take derivative on both sides, so dq dt is, assume C is a constant, C dv dt. So dq dt is the current I. So what I mean is, if you have a capacitor here, if there's a voltage here V, the charge here Q on both sides, they will be constant. However, if the V here change, so if there's a dV dt, you will cause a current flow. So if the voltage change, there will be a current flow from one side to the other side, or vice versa. So this is the meaning of this equation here. Energy, the energy is found equal to half CV square, and U is the energy is stored in a capacitor. So U equal to half CV square, and the unit for U of course is equal to Joule, J. Okay, let's see some work examples. In this example, we plot charge versus voltage. So remember, C is defined as how much charge per each voltage across the capacitor. So if you plot charge versus voltage, so it means Y equal to mx. This is your Y, this is your x. So m, your slope, is your capacitance. So we can say in this case, capacitance or capacitor A, B, C, A has a higher slope. So it means the capacitance of the capacitor A is bigger than B and is bigger than C. So we can say here A is bigger than B, bigger than C. Next, part B. If we have another capacitor 1, 2, 3 that actually corresponding to A, B, or C, but we don't know how they're corresponding. So let's see if we label these three capacitors as 1, 2, 3. The first one has a area A and separation D. So we can say C is equal to A over D. So we can say the C here is epsilon A over D. Now, how about the second capacitor? Now, its area is 2A, have the same separation D. So the capacitance of capacitor 2 is equal to epsilon 2A over D. So it means this is twice as bigger as 1. How about here, 3? It has the same area as 1, but the separation doubled. So this is epsilon A over 2D. So we can say capacitor 2 is the largest, and then 1, and then 3. So if we compare the two sequences, we can say capacitor A is capacitor 2 in part B. Capacitor B in part A is the capacitor 1 in part B. Capacitor C is the capacitor 3 in part B. Example 2, we have 1, 2, 3 capacitors, and we want to find the equivalent capacitance of these 3 capacitors if they are connected in parallel or in series. Okay. A, if the 3 capacitors connected in parallel, so this is 1, 2, 3, they're connected in parallel. We want to find the equivalent capacitor. So C eq. Now in this case, C1, C2, C3, the equivalent capacitor is very simple. It's just the sum of the 3 capacitance. So this is equal to 4.0 plus 9.0 plus 3.0, 16.0 microfarad. B, if the 3 capacitors they are connected in series, C1, C2, C3, you want to find their equivalent. We call the C equivalent. In this case, you must use the reciprocal relationship. It means you first write down 1 over C equivalent equal to 1 over C1 plus 1 over C2 plus 1 over C3. Now again, because all these 3 capacitors, their capacitance is in microfarad, so we can drop this one and we can say 1 over C is 1 over 4 mu plus 1 over 9 mu plus 1 over 3 mu. When you use the calculator, you don't need to worry about using the times 10 to the minus 6. We can just use 1 over 4 plus 1 over 9 plus 1 over 3 and find their reciprocal. So the C equivalent is equal to 1.44 microfarad. Now because they add in reciprocal, so what you find is 1.44 is less than 4, less than 9, and less than 3. This is the characteristic of connecting with capacitor in series. The same formula for connecting resistor in parallel. Number 3, there's a 0.25 Faraday capacitor and 0.45 Faraday of capacitor in parallel. A. Find the equivalent capacitance. So A, they connected in parallel, C1, C2. So the equivalent, C equivalent is C1 plus C2. So it's a 0.25 plus 0.45 Faraday. And this is 0.7 Faraday. B. Find the charge stored on each capacitor and the total charge stored when parallel combination is connected across a 24-volt battery. Okay, so first let's draw this one, C1, C2, and it connected to a battery source. This is 24 volts. So we use the equivalent capacitor here, CUQ. Remember, you must redraw this diagram so it will be a lot more clear. Now what you're asking is, what is the total charge stored here? So the total charge, we can use the formula. It means C is defined as charge per voltage. So Q is equal to CV. Now this Q is the total charge. 0.7, this is the Faraday, 24. So you will get 16.8 coulomb of total charge stored in this equivalent capacitor. Now let's go backward. Because the two capacitors, they are connected in parallel. So one thing for anything connected in parallel is they have the same voltage, just like resistor. So what I mean is the voltage across here is 24 volt. The voltage across here also 24 volt. Now we can find Q1 and Q2 separate. I mean, we are saying going to find here what is Q1, what is Q2. So let's do it. Again, we use C equal to Q over V. So Q1 is C1V. C1, the first one is 0.25 times 24. So 6 coulombs. The same for the second one. Q2, C2V, they have the same voltage. So this is 0.45 times 24. This is 10.8 coulomb. Can you see they are consistent? Because if you add these two, they equal to 16.8 coulomb. This is exactly the total charge we calculate with the equivalent capacitance. Two capacitors, C1, C2, they are connected in series. Find the equivalent capacitance. Okay. C1, C2, I want to find the equivalent capacitance. So this is C equivalent. So we have to use reciprocal relationship to find the equivalent capacitance. So 1 over C equivalent is 1 over 4.0 milli plus 1 over 6.0 milli. So C equivalent equal to 2.4 millifarad. B. If the combination is connected to a 16-volt battery, find the charge stored on each capacitor and the potential difference across each. So let's again look at if you connect the equivalent capacitance to the 16-volt voltage source. So now we have only one capacitor, and remember C equal to Q over V and Q equal to CV. So this C is the equivalent capacitance. So this is 2.4 milli times 16. So the total charge here is 0.0384 coulomb. Now let's look at the charge distribution on the two capacitors. Now if on the total or equivalent capacitor there is a Q here, this is positive, this is negative. So we'll find that on the original two capacitors, this is also Q plus, this is Q negative, Q plus, Q negative. You can think of like this. These two pair of metal plates, when they are connected in series, this part here, if you look at it, they are neutral, and it makes sense because there's no really charge passing through any of the capacitor. So it's just one of the charge will attract to the bottom C2, and therefore the C2 have positive here and the C1 have negative here. So this is the idea. We know the capacitor have the same charge as the total charge on the equivalent capacitor. So we can now find out the voltage across here, because C1 equal to Q over V1. So V1, the voltage across the first capacitor, is equal to Q over C1. And the same argument, the voltage across the second capacitor here, V2 is Q over C2. Okay, let's do it. So V1 equal to Q over C1. Q is the same, 0.0384. And C1 is 4.0 milli. Now maybe we can rewrite this one as 38.4 milli coulomb. So this is easier. So I will use 48.4 milli coulomb. So here is coulomb, this is Faraday, but they're both expressed in milli. So the volt is easy. 38.4 divided by 4, we got 9.6 volt. V2, Q over C2, and the same Q, 38.4 milli coulomb. And the C2 is 6.0 millifarad. So you just use 38.4 divided by 6, and you got 6.4 volt. Now you can check, you add these two together and you will find this is equal to 16 volt, and this is exactly what the voltage. In this capacitor network, there are 4 capacitors, and we want to find the equivalent capacitance. So the idea is, first we find the equivalent capacitance of these two parallel and these two parallel. Therefore, the circuit become 2 here. The first one, it is 0.25 plus 0.40 Faraday. And the second one, because they're connected in parallel, so you just find the sum, 0.35 plus 0.50 Faraday. Therefore, the first one is 0.65 Faraday. The second one is 0.85 Faraday. Now, these two capacitors, they are connected in series. So we want to find the overall equivalent capacitance. And this we can say CEQ. So we use the rule 1 over CEQ equal to 1 over 0.65 plus 1 over 0.85. CEQ is equal to 0.368 Faraday. Next is say to find the charge on each capacitor when the entire combination is connected across a 6-volt battery. So let's do it one by one. First, we imagine this one here is connected to a battery. So this is 6 volt, and the equivalent one is 0.368 Faraday. So we know C is equal to Q over V. So now we can find the total charge in this equivalent capacitance. So this is CV. So the C is 0.368, V is 6, and this is in coulomb. So this is equal to 2.21 coulombs. Now let's go back here, and now if these two circuits connected in series and then connected to a 6-volt battery, and we just found out it means there is a positive, negative, and this is 2.21 coulomb. Of course, the opposite also 2.21 coulomb. So they are equal. Now, this circuit here, and this is positive, 6 volt, negative. So these also have positive, and this become negative. This positive, this is negative. And the amount, they're exactly the same as this one. So what I mean is, this is 2.21 coulomb, 2.21 coulomb, 2.21 coulomb, 2.21 coulomb. The capacitors, they are connected in series. They all have the same charge. And also you can see, if you consider this one here, they are neutral, because one is positive, one is negative. Now remember, this capacitor is the equivalent of 2 capacitors. And now we have to find is what is the potential across this capacitor first. So for this capacitor here, C equal to Q over V, the potential is Q over C. So the potential V across this capacitor is equal to Q over C. The Q is 2.21 and the C is 0.65. So the potential here is 3.4. So this is 3.4 volt. The potential difference across this one is 3.4 volt. Okay, now let's look at the other part. This part. Now this part, the voltage across this one, V is Q over C, and the Q is the same, is 2.21 coulombs, but the C is 0.85. So this is 2.6 volt. You can see 3.4, the first one here, 2.6, the sum is 6 volt. So it means from here to here, this is 2.6 volts. Now once we know the voltage, these two capacitors, they share the same voltage. C equal to Q over V and Q equal to CV. So the charge in this one here, we can call Q1 is equal to C multiplied 3.4. So this is 0.85 coulomb. For this one, we call the Q2 is CV, of course, and this is C is 0.40. The V is 3.4, the same voltage. So this one is 1.36 coulomb. Q3 is CV again. The C is 0.35 and the V is 2.6. This is 0.91 coulomb. Here, Q4 CV, C is 0.5. The voltage, remember, is 2.6, 1.3 coulomb. Now, if we add Q1 and Q2, we'll find 2.21. This is exactly the same number here, and the same here. If we add Q3, Q4, we all find 2.21 coulomb. So they're all consistent. Let's look at what happens when a capacitor connected to a DC voltage source. So we have a DC voltage source in this diagram, which is E. We can assume the voltage is 1 volt, but so when we close the switch, the current start flow here, and the voltage start build up across the capacitor C. So the voltage will start from 0 at this point, and it start increase. We know this actually is V0 1 minus E minus T over RC. This is the voltage across the capacitor. How about the current? The current at the time it closed, I is equal to E over R. It means the voltage of your DC power source over R, the Ohm's law. So this means at the time when the switch is closed, you can think the capacitor is connected just like a wire, but this current will drop. So the current here will exponentially decay, and I as a function of t is equal to the original one, and this is this one, I naught, and this is E minus T over RC. Once the capacitor is fully charged, remember the rule say once the capacitor is about 5 RC, is practically fully charged. So we can open the circuit now, and then now we close here. After the capacitor is charged, it means now the capacitor has a lot of voltage here, and this is positive, this is negative of course, and now the capacitor start discharge. This is discharged. During the discharge process, the voltage across the capacitor will exponential decay, and the current also exponential decay. So this is all the 4 equations describe the 4 cases. Charging, the voltage across the capacitor is V0 1 minus E minus T over RC. The current, this is initial current. I mean, this is like Ohm's law, V over R. But this current will decay exponentially. So therefore we have exponential term here. When it is discharged, both the voltage and the current, they are exponential decay. Now, sometimes people will combine these two into one equation, but I will prefer you just use this set of equations. They're more intuitive. Let's look at some examples regarding to the capacitor connected into a DC source. Example 6, a 22 mil capacitor and a 47 kilo ohm resistor are connected to a 12 volt source. Compute the time constant. So we know the time constant tau is RC, and R is 47K, and C is 22 mil. Now remember the K here is 10 to the power 3. This one is 10 to the minus 6. So when they combine, it's 10 to the minus 3. So we can say this equal to 1034 times 10 to the minus 3. So we can shift this one 1.034 seconds, because this is a time constant. It means it is a time. B. Find the VC and I at this t equals 0, 1 time constant, 3 time constant. Okay, now let's look at the VC first. Now this is a charging, so we should use this one and this one. So when VC, when t equal to 0, and we know it must be equal to 0, but let's do it. 1 minus E minus 0 over RC. So this term is 1. So 1 minus 1 is 0. Okay, and we see one time constant V naught minus 1 when the t equal to 1 time constant, it means equal to RC and denominator is RC. So you're talking about V naught 1 minus C minus 1. So what you get 0.63 times V naught. V naught is 12 volt. This is our V naught. So we have 7.59 volt V free time constant. It means now the T, it should be minus T over RC, but we are saying is the T equal to free time constant. So it's free, each time constant is RC. So we should replace this one as free RC over RC. This is what it means, free time constant. And it should equal to V naught 1 minus E minus 3. And it is 12 times 0.95, 11.40 volt. Okay, let's look at current. The current I at time equal to 0 is I if the capacitor is not here. So you only have a simple resistance. So this is V over R. R is 47K. So you got 0.255 milliamp. I, one time constant. This time is I naught, the initial current, but it exponential decay. When this should be, remember this is the same formula, it should be T over RC, but the T is one time constant, it means 1 RC. So you should just say this is equal to RC. And it is minus 1. And you plug the number 0.094 milliamp. Okay, now I, free time constant. So the same argument, this is minus 3. So this is 0.04978. This is 0.0127 milliamp. Here, part C, it asks you on Excel, plot this against T to linearize the exponents. So let's just do the linearization part and see if we plot this one, what we'll get. Okay, see here, we start from this basic equation. The voltage across the capacitor equal to the DC voltage 1 minus E minus T over RC. And now we do some mathematics. And now we take logarithm or natural log on both sides. And the left hand side, it becomes minus t over RC. And the right hand side, this is log minus so now we rearrange again, and we'll get V0 is 12 minus 1 over RC T plus. So now we compare y equal to mx plus c. So this is our y, this our x. So if we plot y, this one against t, the slope, so we'll get this one here, negative. So it means the slope must be minus 1 over RC, and RC is our time constant. Let's look at this example. A, find the time constant. So tau, the time constant, RC, R is 100K, C is 10 mu. So again, K is 10 to the power 3, mu is 10 to the minus 6. When they combine, you got 10 to the minus 3. So 110. So you got 1,000 times 10 to the minus 3 seconds. And the answer, of course, is 1 second. B, the capacitor is connected in series with the resistor to a 10 volt at t equal to 0. So it is a charging. The voltage across capacitor as a function of t is equal to V0. This is your V0. So this is V0, 1 minus E minus T RC. So now we can put V0 is 10, 1 minus E minus T. We can use the time constant RC, put it here. So this one become 1. And remember, T is measured in second. C, calculate VC at T equal to 1 time constant, 2 and 3 as a percentage of the final value. Okay, so what is the final value? The final value is V0. T equal to tau. So VC over V0. So this is 1 minus E. 1. So when T equal to 1 RC, so this is minus 1. So this is 0.632 or 63.2%. T equal to 2 tau, 1 minus E minus 2. So this is 0.864, 86.4%. 0.950, it means 95.0%. So D 10 volt, if this is for V, so this will be next. If we want to sketch this one as I, okay, so now the I here, we need to find I naught. This is when the time, the moment the switch is closed, and we can just apply Ohm's law, and this is 10 volts divided by 100k ohm. So this is 0.1 milliamp. So if we just say this is in milliamp, this is 0.1, and again this will exponential decay. Number 8, the capacitor is fully charged and then disconnect from the source and discharge across the 100k ohm resistor. So we have a capacitor which is fully charged. It has about 10 volts across. Once you close the circuit, the discharge current will flow through the R. A, the voltage across the capacitor, of course, because the charge will disappear from the capacitor, so it will drop. So it starts from V0. Assume this is following example number 7. So this is 10 minus t 1 second. This is in volts. This is Vc as a function of t. B, from Vc 0.2, 0.4, 0.6. So Vc 0.2, 0.2. So it's 10 times 0.8187. So it's 8.19. I put it here. Volt. 0.4 second. 10 times 0.670. It means 6.70 volt. 0.6. 0.549, 5.49 volt. Okay, how long does it take for Vc fall to 1 volt? Okay, now it means let's solve this equation. Vc as a function of t, 10 minus t over 1, and we want this equal to 1. And it means this equal to 1 over 10, and then you take log, natural log, and t minus t equal to, so t is equal to 2.3 seconds.